Hello, welcome to Type First Application Design. In this section of videos, you will learn how to use F#'s powerful static type system to help you implement requirements correctly and prevent runtime errors. Here's what this section covers. We'll see some advantages of beginning system design by using types to model behavior before we model data. We'll learn how F# units of measure let us avoid computation errors by giving numbers strongly typed meanings. In the next video, we'll expand that idea and see how single-valued unions let us transform any built-in .NET data type into a domain-specific type. The final video wraps up this section by showing how we can use types to prevent code that might produce runtime errors from compiling. These techniques will help you build systems more rapidly and with higher quality. So, welcome to Designing Behavior Before Data. In this video, I'm going to first explain what type-first design is and how it compares to another popular software development practice, test-first design. Then I'll discuss how using F# types to model behavior helps you capture the most important requirements first. Then I'll demonstrate these ideas by showing how we can start a design process in Visual Studio. You'll recall from previous videos that a type is anything that can be passed into or returned from a function. F# is a statically typed language, which means the F# compiler won't compile code if it detects that the code allows incorrect types to be passed into or returned from functions. So, type-first development is the practice of defining our types to capture as much information about the system's requirements and responsibilities as possible. That way, if we write code that could make the system behave incorrectly, the code won't compile, and we won't need to wait until runtime to find the error. If you practice type-first development, you'll have less need to use another popular programming practice, test-first development. In test-first development, you express the requirements of the system by writing tests. The tests fail, and you make them pass by writing code that satisfies the requirements. Test-first development is essential if you use languages like Smalltalk and Ruby that don't have static typing. But it's less essential for languages like F# that do have static typing. Now, I'm not saying that you'll never need to write tests with F#, and we've already seen that F# has strong support for unit testing. But I prefer to catch my bugs at compile time rather than runtime if I can. Now let's talk about why we'd want to model behavior before data. When we're designing software, we depend on subject matter experts to tell us what the system should do. We've grown accustomed to the idea that we should talk to the experts using their own ubiquitous language. And frequently, experts express the most important requirements in terms of behavior. They say things like this: to open a checking account, a customer submits an application, 2 forms of identification, and an initial deposit. If the pressure inside the mixing tank exceeds 90% of the tank's rating, the mixer must shut down. Now, these statements don't tell us exactly what data belongs in a bank account application, or what the maximum rating of a mixing tank is. But if we can capture these behaviors in code early in the design process, we'll have gone a long way toward satisfying the system's requirements, and we can fill in details about the data as we learn more about the behavior. Let's see how this can work in practice. I'm going to start with this empty F# project, where I've written one of the requirements that I just showed you. We're going to start implementing this requirement by writing a function called openCheckingAccount. So I've just said that the function takes 3 arguments, application, ID, and deposit, and returns unit. We evaluate that, we see that the F# compiler is content to not know what type the arguments are, it just treats them as generic. But we haven't really captured the fact that this function is supposed to create a checking account. So let's change it to say that it does return a thing called a checking account. Now we get a red squiggle saying that the compiler doesn't know what a checking account is. Well, so far, neither do we. But we know that a type called checking account must exist. Fortunately, F# lets us define this type without knowing anything else about it. All we have to write is this: The notation that we see in F# Interactive tells us that checking account is actually a single-valued discriminated union. That's what this vertical bar here means. In fact, I could have written the code that way, like this, and even indented it the way I normally would with a discriminated union, and I get the same result. We'll see more uses for single-valued unions in a later video. But for now, let's use the same technique to assign types to the 3 arguments to the function. Notice that here I've taken the opportunity to capture the requirement that the user is supposed to provide 2 forms of identification. So I've made my ID parameter into a tuple, which consists of 2 instances of this type identification. Now let's suppose I get an additional requirement. The deposit must be at least $500. I can implement this by evaluating my deposit argument inside the function and returning an option to indicate whether it's satisfied or not. But of course, I can't compare a single-valued union with a decimal number. There are several ways I could resolve this, but I'll choose the simplest way, which is simply to change the definition of the type deposit so that it becomes a synonym for the decimal type. And now it's possible to compare a deposit value with a decimal number. As we proceed with adding more behavior to the function as we learn more requirements, we will discover that we need to add additional data to these types that represent the arguments, so we can modify the type definitions as needed, but always in accordance with what behavior of the function requires.